Thanks. My name is Jakub. I'm the founder and CEO of Zeta Alpha. And with Zeta Alpha, we basically built RAG and agentic AI systems for companies to deploy on their internal knowledge, on complicated documents internally. And I've actually worked in AI and search for more than 30 years now. So I'm kind of an NLP and search person. And kind of in all of those decades, when talking about multimedia content, talking about images, we've always kind of brushed it aside a little bit. Yeah, there's images in documents, but there's computer vision, you know, and they will take care of it. And that has radically changed in the last 12 months or so. So basically, in the last 12 months, GPT 4.0 came out about May last year. And basically now these large language models have become vision language models, and that's made a radical change in what's possible with multimedia content, and also in the context of RAG. And basically there's been a lot of breakthroughs, and that's why we thought it couldn't be more on time, because actually from our customers, we're seeing a lot of demand for actually working with PowerPoint slides, charts, tables, all of these things in their documents. So we started a research project, or kind of research and development project together with Batu, and he's going to give the most of the meat of the talk.
Yeah. Hello, everyone. I am Batu. I'm an AI research intern at Zeta Alpha. I am studying AI master's degree in the University of Amsterdam. So what interests me most about visual document retrieval is visual language models are the most cutting edge of AI. It's the state of the art. And information retrieval is one of the most practical approaches and use cases of AI that we have. And how these academic research translates to actual practical use cases, and we do that with OpenSearch.
I'll give a little bit of an introduction before Batu will give you the actual really deep content of this talk. So with Zeta Alpha, we're local here. We're based in Amsterdam on Science Park, just a little bike ride from here. We have been working on our AI platform for the last 5 years, and we're basically helping expertise or knowledge-intensive companies like BASF, Festo, Deloitte, which have very complicated internal knowledge in many, hundreds of thousands of unstructured documents, to build customized RAG and generative AI solutions, and these days also more and more agentic AI solutions on top of that proprietary internal confidential content. So this is what our platform looks like. So basically you can ask a question, a complex domain-specific question, like here from the chemistry domain, and you get a generative AI answer, but it's grounded in the internal documents of the organization through these sort of links and citations. And well, there's a lot more to the platform, which I won't go into now, but basically it's a way to discover and organize internal knowledge, and not only connect you to answers for your questions, but also connect you to expertise inside and outside of the organization. So we are very OpenSearch centric, so we have embraced OpenSearch, I think almost 5 years ago, because at that time it was the best implementation of vector search, which actually also combined vector search with more classical search engine features that are necessary to build for the enterprise. Our platform is an end-to-end set of services ranging from ingesting documents from all kinds of information sources, whether it's popular applications like SharePoint and Confluence and Slack, to customized data stores in legacy applications. We process them. I'm glad we are coming after the RAG talk in the previous session. We process them in this sophisticated ingestion pipeline, where actually more and more we're also seeing customization play a big role, and LLMs be a big part of the extraction of metadata out of unstructured documents during the ingestion process. Then, of course, a big part of it is vectorization, so creating semantic representations for chunks and passages. And we see that in many cases it helps to really focus on the R of RAG and fine-tune domain-specific models for particular industries and knowledge domains. And then finally, the application that I just showed you in the previous slide runs on a set of APIs powered by our search and agent services. So the workhorse of this is really RAG, Retrieval Augmented Generation. I think by now most of you are familiar with the pattern. A user asks a question. That question is not directly related to knowledge that is part of the trained knowledge in the LLM. So to mitigate that problem, you pass the same query or a variant of it to a search engine, and you retrieve internal knowledge or up-to-date knowledge from your search engine, and then you provide those passages as context in the prompt of the LLM, and now it becomes very easy for it to give a correct and grounded answer. And of course, with the rise of this RAG pattern, vector search has really become very prominent, mostly because questions and answers are lexically usually not very related, so you need to use text embeddings for that. Well, I think we're also all pretty familiar with how text embeddings work. So you encode documents as a vector by running it through a neural network, a transformer-based model. And then if you have a query like self-driving, a document that contains the word self-driving car, and you have a question that asks about autonomous vehicles, these vectors will be mapped by the embedding model to a nearby region of the space, and that will allow you to find the right document. So that's the workhorse of RAG in the system. And why does that need to be multimodal? Well, there are many types of documents which contain a lot of visual content. For example, if you're talking about in industry manuals of complex machines, they will of course have photos or diagrams of the machines, and then under it text that explains what the machine does and how to troubleshoot it. Or if you have a, it's not very readable, but here you have a research paper about some complex chemical process. Of course, it will contain diagrams with chemical formulas or process flows, and you want to ask questions about that. Or in many domains, maps are super important, right? So, for example, in mining, the location, sort of geolocation is everything, really. The whole content of the document is only relevant when you are able to relate it to its location on a map. Or you will have graphs or complex diagrams of inventions, for example, in patents. So the vision language models like GPT-4o, of course, allow us to chat with image content, because we can just provide image content as payloads to the prompt of vision language models. But how do we do the R part, the retrieval, the search part of RAG? If only we could embed images just as well as text. Well, we can, of course, since the days of CLIP, which was already about 4 years ago. We have this way of finding a joint representation. Basically, we take a text encoder and an image encoder in CLIP, and by using this contrastive loss training, we can basically take the representation from the vision model and from the text model and align their position in the space just like we would be training a regular dense retrieval model. So these models like CLIP are trained on very large sets of multimodal pairs. So basically you have aligned images and descriptions. And using this contrastive loss training, you can basically take any computer vision model and any text encoder and get a shared representation space. But there's a lot of problems with this approach. If you take a separate vision encoder and a separate text encoder, that vision encoder is trained for a different purpose, and it might not represent correctly all the details in the image. One thing is that you have a single vector for an image, which can be a problem for very complex images. There's a lot of text in some images. If you talk about graphs or tables or patent descriptions, and CLIP is not particularly good at kind of OCRing, reading all the text in the images. It's not actually trained to answer very complex questions about the image, so it fails on complex relationships and details. And last but not least, it will always find something, right? So with a vector, there's always a vector nearby, so you have no guarantees there. So beyond CLIP, large language models have really become multimodal in recent years. So if you look at the architecture of large language models, something like GPT, basically the single modality models like GPT are trained to predict the next word based on a sequence of language tokens, and it's trained, to generalize on very large amounts of data to extract sort of the semantic underlying structure of the language. And vision language models are actually a very simple generalization of that, that don't introduce a separate computer vision model, but simply present patches of images as tokens in the same framework of GPT. So basically next to the text tokens, you're also introducing visual tokens, which are small patches of the image. And then you train the whole generative model in the same way as you would train a regular GPT model, but it actually allows the model, by being trained on more complex visual question answering tasks, or even OCR. You can put here a page of text and here the textual representation. You can actually train it to develop internal representations which are super powerful and representative of the content of the image. And GPT-4o was the one that most of us first got to play with. There are many different models, also open source now, which allow us to take the weights and to actually use these models in a way not only to answer questions, but also to do other things, which Batu will be talking about. So the first approach to actually use these vision language models to allow us to search for images is very simple. We can take the image and prompt the model to describe the content of the image, which is an approach that we call captioning. So basically we can get a simple description of this image. It shows the interior of a modern multi-story office or institutional building, but using prompts we can of course make that also much more detailed and rich, describing the plans and the staircase and the type of building. And then we can use a traditional text embedding model and use that as a pseudo image embedding and have multimodal retrieval. But much more sophisticated approaches have emerged. This is a paper by Manuel Weiss that got published in June of last year, called ColPali, Efficient Document Retrieval with Vision Language Models. And it was kind of a revolutionary new approach, because basically Manuel Weiss and his co-authors proposed to use a vision language model to completely eliminate the traditional information retrieval pre-processing pipeline. So basically, instead of going from a PDF and then, chunking the PDF and extracting the tables and figures and processing all of that separately, they proposed to just take an existing vision language model that was trained, among other things, for visual question answering, and to simply use the representations that it generates directly as a embedding for the content. So basically going from a bitmap of the page to embeddings in your search engine. And in this picture here, you can see that the traditional pipeline with using a PDF parser is not only very complex and hard to maintain, but it's also very slow. It actually takes about 7 seconds to process a PDF, whereas with this ColPali model, it takes only about 0.4 seconds. And they showed that basically not only this radically simplifies the pre-processing pipeline, but it allows you also to answer very complex questions about, for example, this graph here. So the question is, which hour of the day had the highest overall electricity generation in 2019? And by looking at the image patches that it's actually retrieving, you can see that it's really reading the axis of that graph and then kind of finding that reasoning about the visual information. So that's very cool, and it got a lot of people thinking differently about this problem. But not only is it very cool, it also works very well. So if you in the paper they showed that if you contrast this approach with the more classical retrieval methods based on text transcriptions of these documents or based on clip models, that ColPali actually pretty much blows all of these approaches away on this benchmark. Batu will talk more about that benchmark. So a bit of dive into the academic literature. So ColPali is actually based on a model called ColBERT, which is a textual retrieval model, which basically stands for Contextualized Late Interaction on BERT Models, published almost 5 years ago now by Omar Khattab and others. And basically, the idea of ColBERT is that for a query in a document, you're going to create embeddings for every single token of the query and all tokens of your documents. And that at query time, you're going to retrieve for every token of the query the nearest vectors from all of your documents, and then compute this late interaction formula. So it's quite computationally intensive. Around the same time, a different paper got published called DSE, which stands for Document Screenshot Embeddings. And that's actually a very different approach. It takes the same kind of vision language models, but instead of doing late interaction with separate embeddings for every token of your query and document, which is super expensive, it only creates one embedding for a document or a chunk based on the stop token of the same vision language model. So they are very similar, but very different computationally. So Batu is looking into how they actually compare in accuracy and efficiency, and he will pick it up from here.
So let's start with the theoretical performance. This is the best case. This is without doing any retrieval. This is just computing the scores on Vidora benchmark. And let me start with explaining the Vidora benchmark. This is proposed by the ColPali authors. This is the go-to visual document retrieval benchmark. It specifically has visual questions that can be answered from visual things in the documents, such as like plots, diagrams, stuff like that, not from text. It's specifically focuses on those type of questions and has around 10 data sets in it. Some of them are synthetic data sets. They are the one that performs the best. So the questions there will be synthetically generated. And some of them are natural data sets. For example, Archive QA, this is, as you know, probably Archive, the research paper site, diagrams from that. DocVQA, again, diagrams and plots. InfoVQA, slides, plots, those kinds of things. These are only visual information. And then, for example, we have Shift project, which is a proper PDF document with a plot and a bunch of text in it. And as we can see, we have ColGwen2 and ByGwen2. The call model represents the late interaction model, and by model, the ByGwen is the by-encoder model or the DSE approach here. And these are the exactly same training, so exact same training data models. And as we can see, ColGwen on average performs around 5% better. But for Shift project, it's around 10% better, and we'll come back to that later. So this is the ideal case for late interaction. So let's dive into OpenSearch. Doing DSE with OpenSearch is, I would say, pretty straightforward. So each document page, that would be one image, would have one embedding, and that would be indexed as one document. We can use any approximate KNN you like. You just embed the document image and then put it into the index and do your retrieval. But when it comes to late interaction, we have some challenges. So here's our query. Why is late interaction hard? First of all, you embed the query, but now you have n query tokens, which means you have n embeddings. Now you have to do n searches per query embedding instead of just doing one per query. So this basically multiplies your queries by the query length. Then you have another challenge. The documents are also multiple embeddings. So with the ColGwen models, I think, yeah, it's around 740 embeddings per a single page document. So that basically multiplies the vectors in your index by 740. For average of 500 documents for the data sets in Vidore, it turns out to be around 370,000 embeddings, which is quite a lot and slows down things massively. So then there's a third problem. Now you have n responses per query token, and how do you aggregate them? So this is the basic approach that first comes to mind. Use a flat index, so no nested embeddings and stuff, and do approximate late interaction. I'll come to the approximate part now. So let me explain the late interaction a bit more in detail. So for each query, you get, for each query token, you compare the document, you compare with every document token in the document. You get the maximum similarity with that query token, and that would be your document score for that query token. And then you do that for every query token, aggregate them, you get the total document score. So that would be too many computations. A way to approximate that would be, since this is a flat index, get the global top K vectors, which would be nested vectors, not the document level ones, and then use those for the max similarity comparison. So you don't actually see all of the document vectors, but you only see the top vectors globally. And then you use approximate KNN to get those. And a key point is you use msearch to parallelize your queries, because you have to do many queries per query token. So those subqueries need to be parallelized. And then you aggregate the responses client side. So this is a bit of a controversial topic maybe. Since we only return the scores, the thing we return is not actually that big. But if we decided to return all of the embeddings that we retrieved, the response would be too big, and we can't really return that in a reasonable amount of time and do the aggregation client side, but we can do it with the scores. So a bit more interesting stuff, the nested index. So this time, each document is a single document with 740 nested embeddings. So we use a nested query to match these. The size in the nested query there with n would be how many documents, top-level documents, parent documents, so how many pages that we return. And the k at the bottom would be how many nested embeddings that we search through. So what we are actually doing here is that the nested embeddings would score the documents by the maximum similarity nested embedding. So what this will do is get the scores of all the nested embeddings, get the maximum, and then assign the maximum to the document score. So what we return is the ranked document scores corresponding to the maximum similarities, which is pretty much late interaction. The key here is we are not actually doing it over the entire data set. So that's where the approximate part comes in. So we again do the aggregation client side. So because scoring scripts sometimes conflict with ANNs. And then if you want to make this equivalent to full late interaction, we have to make sure that the number of documents that we are retrieving is the entire set, and the k nested embeddings that we are searching through is all of the embeddings, which is an insane number, and k is limited to 10,000 in OpenSearch. So we can't actually do full late interaction, even if we want it on a reasonably large data set. So again, remind we have 740 vectors for a single page. So what do? We use late interaction as a second stage. So here is a two-stage retrieval query. We use the average embeddings as our first stage. This is just arbitrary. You can use anything else you want. And then we get some candidates from there. And then we rescore with the late interaction. Since now we have a lot less documents to rescore, our late interaction performs a lot better. So it's much less of an approximation and is a lot faster. So a bit of a comparison with other search engines. So how does Vespa do it? They use BM25 as the first stage retrieval. Well, that means you have to have a text representation. And kind of the point of ColPali was removing all that text, OCR, pipeline, all that stuff. So if you have text representations, it kind of contradicts there. What Elasticsearch does, as you can see, I borrowed the average document embedding from them. They use the average documents for the first average document embeddings for the first stage retrieval, and then they do token pooling to reduce the number of embeddings. They borrowed it from ColGwen or ColPali's original approach. So that would reduce the number of embeddings per document at the cost of some performance. And what both do is binary quantization with inverse having distance as similarity. So you can also quantize your vectors if you want with OpenSearch. It's complementary to what I just told. So let's get into some numbers. In terms of efficiency, bi-encoder, meaning the DSE approach, is by far the most efficient one. The retrieval speed is around 8 milliseconds. There are just 500 vectors per 500 documents, and it takes around 12 megabytes to store them. Then the flat approximate late interaction. This was the flat index without any nested documents. So as you can see, it's a lot slower. The main reason is you have to conduct many queries per late interaction query because you are doing it for every query token. And this is also including the aggregation scoring, the summation time. So it's around 185 milliseconds and a lot more vectors, 370,000, and meaning a lot more space to cut. So it's around 700 megabytes. So the nested one is a little slower. So it's 210 milliseconds. Again, the same number of documents, slightly larger storage. And this two-stage one is, again, a little slower, 266 milliseconds, around the same embeddings and around the same storage. But how do they actually perform in terms of performance? So effectiveness. We are back to the Vidora 1 benchmark. So this is the average performance across all datasets in Vidora V1. So these are the base models that we used. For the bioencoder, we used BioGven2, and for all the late interaction models, we used ColGven2. We measured with NDCG at 5, recall at 1, recall at 10. We believe these are some important metrics because even if you are doing RAG, recall is not the only thing you need to consider, because if you are feeding wrong information to RAG, it will affect the performance quite badly. So that's why we also include NDCG at 5 to see that the correct vectors are scored highly. So bioencoder actually performs quite well, has the best recall at 10, also, although it's a close margin. The flat index approximate late interaction, I would say not a good approach. It's fast, but bioencoder is faster, and it's outperformed by the bioencoder. The nested approximate late interaction performs a little better, but again, as I said, you need a really good first stage retrieval to actually make this perform, because right now it's using not too many vectors, so it's not good enough of an approximation. So if you do it with a two-stage retrieval, the first stage retrieves the vectors, and then you kind of do the re-ranking or the scoring with the late interaction. It unlocks the potential of late interaction much easier, makes it much easier to unlock the potential of late interaction pretty much. So what do we have? We are back to this plot. So this plot is comparing the theoretical performance that we talked about versus the actual practical performance that we got. As you can see, the transparent parts are the potential performance we mentioned. So the orange one, meaning the BioGven model, the DSE approach, doesn't really lose much on the performance, potential performance. But the late interaction model, ColGven, loses a lot of its potential and even falls behind BioGven in some data sets. And the 5% performance gap is pretty much eradicated except for the Shift dataset. So what's going on there? The Shift project dataset. Well, as I mentioned, it's a text-heavy dataset. So a single image patch has a lot of small details that it attends to. There are small text in it. So if you reduce the number of the embeddings, you are kind of losing some of that detail. So that's why late interaction performs better there, and bioencoder struggles. So how can we address this? Well, back to text embeddings and captioning. Here, we have the ColPali paper as an example. So we extract the image and text from the document. So we are back to the text extraction OCR pipeline. We feed the image to GPT-4o Mini for captioning. But a key thing is we also feed the text to GPT-4o as context to improve captioning performance. We get the caption and the text, we append them together, feed it to our text embedding model. In this case, we use Arctic Embed Large V2, which is quite a good text embedder. And we use the same approach as bioencoder for the indexing. So right now, we converted this image into caption along with text context, and now have text embeddings. So how does it perform? Surprisingly, it's actually better than BioGven2. In terms of efficiency, it's same as BioGven and DSE, even though it has a little lower dimensionality. The performance, as we can see, is still less than ColGven, because we are pretty much using just one embedding for all of that detailed text. And another downside is it's quite inefficient with embedding the documents, because right now we are using GPT-4o Mini instead of just Bio or ColGven, which is a 3 billion parameter or 7 billion parameter model. So this is an intermediate approach that you can use. So what should you use? That's the main question. If you want the best performance, you can go with late interaction models, ColGven, but it wouldn't be as scalable, and you need another first stage retrieval, but you will have the best effectiveness. If you want an in-between approach, you have the BioGven, And if you want to kind of have a quick solution that works well with text-heavy documents, for example, PDFs, then you have the text captioning that you can also use with your existing text pipelines. But for example, a slide data set that has less text-heavy would be better suited for Bygwen. So back to Jakub to show how we use it.
Yeah, so just one more slide, but that's really kind of the where's the money slide. So obviously a lot of this is very processing heavy. So how do you make sure that you get some of that money back? Well, if you have a potential, if you have a customer and they give you their many thousands of internal PowerPoints, and then you get a test set, and you really have to compete against other vendors in the market on that test set, and they ask you this question: how many US original scripted TV series were there in 2017? We were shaking a little bit when the demo came up, and we had just implemented these kind of methods, and the answer was 487 with a little citation here to point to the single document where that answer was found. And guess what? We clicked on that citation link, and we ended up on slide 7 out of 10 of this deck. And it actually had this graph, and 2017 had the number 487. And that was our win against all the competition in this client. So, yeah, this stuff really works. So kind of summarizing the main points of our talk, we are now living in the age of vision language models, and multimodal RAG is here today. So there's no longer a reason, even for old natural language processing and search dinosaurs like myself, to sweep visual information under the carpet. VLMs are actually today powerful enough to add value to RAG systems. Yeah, Batu, you did a lot of experiments, so would you say that vision can replace text completely?
Not yet, but might be possible in the near future.
What is the near future?
I would say within maybe 2 years. Maybe too ambitious, 3, 4, something like that.
All right, so I think ColPali has really shown a very innovative approach to reshuffle the whole retrieval pipeline. Obviously, with the multiplication factors in the amount of embeddings and vectors that you get, there's still a lot of research to do to reduce that. And you see that basically the gap between ColPali and DSC and captioning is not so radical if you look at the search relevance. So yeah, trade-offs have to be made and things still have to be invented. I think the Col models are kind of overall the most effective, so they have the highest relevance score, but they're also super expensive. And right now, the bi-encoder, DSC style models offer a very good middle ground. And if you're looking for a quick fix, captioning is very good for text-heavy documents and also for visual question answering. And yeah, it works today in OpenSearch, as Batu has shown.
Yeah, with just some small tricks. You have to use msearch to parallelize the subqueries, and you have to use approximate KNN to scale it, and then you can use client-side aggregation to just aggregate the scores, not pass the whole embeddings.
Right, so that's it. If you're interested in these kind of advanced R&D topics in search and AI, you can check out our Trends in AI monthly webinar series, which is presented live here from Amsterdam once a month. The next one is next week, Friday. And our slogan is enjoy discovery. And if you have any questions, we're open to take them. Thank you.
Microphone.
Ah, no time for questions? Okay. Questions outside after.
Yeah.
One quick one?
Okay, sure. Yep. Hey, thanks. That was a great talk. So, in your experiments, like in the two-stage retriever, right? So one of your experiments. So, what was the pooling setting for your query tokens and your document tokens?
What do you mean?
What was your pooling setting? Like, say, in your two-stage retriever experiment, the last one that you had in your benchmark.
Yes.
What was the pooling setting? Was there any pooling setting in the first place? And if it was, what was the pooling setting for both the document side and the query side?
We didn't really experiment with pooling settings there. So,
Okay.
yeah, it was just...
Okay, it was like for everything was parallelized and there was a KNN search for every query token.
Yeah.
Okay. Thank you.
Thank you so much for an amazing talk. Yeah.